Thanks for the invitation. So working for SINTEF, I see myself as a researcher, but most of my projects are closely related to industry. And I'll try to provide a combination of the challenges that we see in industrial AI, some success stories, and some lessons learned. So I don't know about you, but outside my professional life, I'm daily interacting with various kinds of AI. And it's not because I'm chatting away with chatbots. In most cases, it's so seamlessly integrated that I hardly think about it as being AI. So Google is helping me when I search for information, Amazon's suggesting additional stuff that I don't need, Facebook automatically tags my friends in my photos, and AlphaFolds determine all the proteins foldings. Okay, to be honest, I don't interact with AlphaFold on a daily basis, but it's still super impressive. At the same time, according to Gartner, about 80% of AI projects, they never reach deployment. And of those that do, they're only profitable in about 60% of the time. So this failure rate of industrial AI projects may seem a little at odds with my previous statement of daily interacting with AI. And I assume that most of you here are working with machine learning or AI, and you know that it can be challenging. But really, are Facebook and Google so much better than everyone else that they can make it work seamlessly when few others can? Or is there a fundamental difference between what they are doing and industrial AI? Well, industrial reality is complicated. Often industrial plants, they're complex systems that were built a long time ago, and then they've been continuously developed over a long time. So this may easily become sort of a mismatch of systems. It also means that even within the same plant, the same task can be solved in 2 or more different ways. And when the same plant can solve the same task in multiple ways, you can try to imagine the level of standardization across different sectors. So from a machine learning perspective, that means that every problem is, at least in most cases, it's unique. And even though there's a lot of available tools out there, it's not always just plug and play, because you need a lot of adaptation. Also, machine learning and AI depends on data. Industrial data comes from sensors, or even worse, it comes from manual measurements. They're noisy, they're sparse, they have offsets, they have drifts, and they may not even measuring the quantity you're actually interested in, because that may be something that happens in an environment where you cannot put a sensor. It might melt or it might deteriorate in some other way. And on top of this, the industrial systems, they're often safety critical, which sets some requirements for precision and trustworthiness of any model to be used with the system, not only just machine learning models. But if it is so complicated, why should we bother at all? Well, industrial models, they're quite often referred to as digital twins. They can benefit significantly from machine learning to model all the parts that are hard to describe analytically. And we do need those models, because the global society faces tremendous challenges in terms of climate and biodiversity. And many industries, they can become greener by reducing waste or using resources more efficiently. But this requires really good understanding of the system and good models of the system to do some sort of optimization. And of course, often for the industry, there's an additional motivation in terms of economical benefit from reducing your waste and increasing your efficiency. So in a sense, it will also help making them more competitive. So rather than talking about failures, today I'll try to give 3 brief examples of successful implementation of machine learning in industry. The first one is on electricity, which seems to be a hot topic these days. And many people seem to have an opinion about it, which often comes with very little insight into the market. In this innovation project with Skagerrak, Evenue, and Equinor, we have focused on predicting volumes rather than prices, but of course the two are connected. So electricity prices, they are decided 1 day in advance in the so-called day-ahead market. And that's the one everyone is discussing at the moment. They are affected by many different factors. They're affected by the solar and wind production. They're affected by the weather. The consumption is affected by temperature. The frequency capacities in the transmission grid has a lot to say. Oil prices, trading, human factors, lots of different factors. And they can only be predicted with a certain precision. So there's always the need for adjustment on a shorter time scale than the day-ahead plans, and that's called regulation. And in this project, we attempt to predict these adjustments based on the original plan, the bottlenecks in the transmission grid, and the weather data. And so far, we have 2 different models. One is a ResNet-based model on weather images, and the other one is a graph-based neural network capturing the information from the bottlenecks. And neither of those two models, they have spectacular performance at the moment because of the complexity and the amount of noise on the data. But they're both much better than random guessing. And currently, the way it happens with this regulation is that the people making the decisions, they have a gut feeling, look a little bit at the data, and then they make some decisions. So a model providing them some data-driven support will definitely fill a gap in the daily routines of the partners in the project. The challenge in the project is the complexity of the system, whereas the keys to success are partly the amount of data that we have available, and partly using what we call hybrid modeling, or at least enforcing as many known relationships on the data, for instance, via the graph structure representing the transmission grid. The next example is a really cool project we have with Skanska, where we're trying to reduce the CO2 emission, the cost, and the time for road construction. And this will be achieved through a better coordination of the machinery. But to compute this optimal plan for the machinery, our optimization algorithm needs a description of the construction site. But that's naturally changing over time. They're building a road, and consequently, it's something that we have to map dynamically. So Skanska, they have equipped all their machines with iPads in order to better communicate with the drivers. But we exploit these iPads to get GPS data, and then we use a combination of unsupervised learning and other methods to generate dynamic maps that can be utilized in the optimization process. And in addition to that, we do some supervised learning to predict fuel consumption for the suggested solutions, which is directly related to the CO2 emission. And again, crucial aspect of the project has been data and access to data. But this project has also significantly benefited from taking out smaller results along the way and setting them in production. And from an analysis perspective, some of these results, they're actually pretty simple. But they now provide data-driven support for the day-to-day decisions on the construction site. And the last example is on condition monitoring of maritime propulsion systems, where Brunel, they're currently developing or deploying a series of machine learning-based algorithms to detect anomalies in ship thrusters around the world. The philosophy of condition monitoring is to provide service when needed, not before, not after. You don't want to fly an expert across the globe to do unnecessary maintenance, but it's also expensive if you wait until the equipment breaks. So you want to find the balance. The standard way to look for anomalies is to learn what an anomaly looks like. Brunel, they have made a huge effort in collecting and structuring their data, even before we could start analyzing it. But there was no labeled anomalies. It's not so that there's no anomalies in the data, it's just that they're not labeled. So that started an iterative process of learning what normal looks like. Identify potential candidates for anomalies, then get the experts to verify or reject them, and then start all over again. So now the final algorithm consists of two parts. It has one part, which is a supervised model that only knows normal, and then it flags all the anomalies. And then there's actually a fairly simple rule-based model that classifies them afterwards. So apart from, again, data being crucial in this project, and another very important component is the access to expert knowledge. I will finish off with a few points that we have seen as keys to success in industrial AI projects. They come in random order. They're probably neither unique nor universal, but they do go across a range of projects and probably beyond industry as well. And they're complementary to what Torgeir mentioned earlier. So first of all, artificial intelligence is not intelligent. Actually, machine learning mostly works well when you already know the answer. For supervised learning, we need the answer in terms of training data. We need data with known outcome for training. But in general, the more knowledge we have about whatever system we try to model, the easier it is to construct a meaningful model, and the easier it is to verify the performance. It's also hard to do data-driven modeling without the data. And the data must have the information about whatever you want to model. A third key point is to focus on value. Formulate the problem based on value creation, not on wanting to do particularly something with machine learning. It's a method, it's a tool. You have to think about what's really bothering you in daily life. Where do you think you could create? Which problems do you think you could create value from solving? And then the next step is to decide, can machine learning actually provide a solution, or are other methods better? Start simple. Don't aim for the moon. Start with the small steps, even if the first step is just getting the data sorted out. Machine learning models, they are powerful and flexible, but that also makes them vulnerable. They're vulnerable to the lack of data in terms of quantity and quality. And they're vulnerable because in practice, they will work as a black box model, in particular when we talk about industrial machine learning, which is rarely compatible with safety requirements. So there's no shame in choosing a simple and robust model. And if you have knowledge, use it, domain knowledge. Exploit the flexibility of the machine learning combined with the robustness and explainability of classical models. And this is also an encouragement to data scientists and researchers working with industry. Never underestimate the existing knowledge. So I hope that I have shown that there is value and purpose for machine learning in industry, but also a lot of challenges to address, and most of them require a collaborative effort to solve. So thank you for your attention.